I'm going to talk about small constellation theory in a cylindrically hyperbolic groups. So the purpose of my talk today is to convince you that the cylindrically hyperbolic groups is a useful class. You can do something with them. Not only they include a lot of examples, but you can actually prove meaningful theorems about them. And I'll say a few words about. So I'll start with general philosophy. So the general philosophy of small constellation theory is the following. So this is not a real theorem, but that's what we want. Suppose that G is hyperbolic-like group. And you pick some elements R1, Rk, which you think of as relations in your group, which are sufficiently independent then the quotient group G modulo the normal closure of these new relations is hyperbolic-like normally in the same sense as the H group. Locally looks like the original group G and is as nice as G was. So, well, now you just have to make everything precise. So you take your favorite meaning of hyperbolic-like, and then you try to find a condition which captures this property of being sufficiently independent, so the conclusion you want holds true. And now, hyperbolic-like is already specified, and locally looks like G normally means that the map from G to this quotient group can be made injective on arbitrary finite sets, and sometimes even on some infinite sets. So locally, taking this quotient doesn't change the group. And as nice as G was normally means that if G was a nice group, for example, torsion-free, then the quotient will be also torsion-free. So whatever nice property of the group G enjoys, you can transfer it to the quotient group. There are no new pathological things happening in the quotient group. So this philosophy goes, well, if you start with free groups, then that's classical small constellation theory, which goes back to Linder. And then for hyperbolic-like settings, there are several people who, so for hyperbolic groups, the whole story starts with the paper by Gromov, who stated a theorem like this. It wasn't quite correct, I mean, it was wrong with Victor, but the idea was exactly like this, and the idea was absolutely correct. So it was made precise by Olshansky, who stated the correct theorem and proved it. And then there were, so for hyperbolic groups, then there were several generalizations by myself for relatively hyperbolic groups, and the next step was done by Michael Hall for cylindrically hyperbolic groups. So I don't want, well, there are lots of theorems like this, and in some sense, there is no universal statement which you can use in all situations. You need different theorems in different settings, depends what you want to do with this thing, with this small constellation theorem. But I will try to avoid, so I'll try to give an exposition which avoids some technicalities related to this sufficiently independent condition. And I will try to make it as easy as possible, so that you can apply some results which follow from small cancellation theory without actually knowing how they are proved, how this small cancellation condition works. So in my talk, from now on, I will not mention the small cancellation condition related to the sufficiently dependent condition at all. So let me state one instance of this theorem, which is for, so now it's a real theorem, and I will state the result through my Michael Hull. So for me, now hyperbolic like means acylindrically hyperbolic. So that G, B, and acylindrically hyperbolic group that is well, you remember one of the equivalent conditions in the definition of acylindrical hyperbolicity, or in the theorem which I stated, was that there exists a generating set X of G such that the K-graph of G with respect to X is hyperbolic, non-elementary, which means that its boundary has more than 2 points, and acylindrical, which means that the action of G on the scale graph is acylindrical. So then, right, now, I need a notion, which is, I need to state the theorem, I need to introduce another notion, write the definition here. So suppose that G is an acylindrically hyperbolic group, and S is some subgroup of G. So that S is called suitable if first S is non-elementary, what it means, so if G is acylindrically hyperbolic, it admits an acylindrical non-elementary action on a hyperbolic space, right? We just use this definition. And S non-elementary means that S acts non-elementarily on the same space. So the reduced action of S is still non-elementary. And second, S does not normalize any finite, non-trivial subgroup of the group G. So this is an algebraic condition which somehow cannot be avoided, and it makes everything easier. So this is my definition of a suitable subgroup, which will occur in this theorem. Here is an example. If G equals, say, just a free group on 3 generators, A, B, and C, and S is a subgroup generated by A and B, then S is suitable here, right? So this condition automatically holds true if the group is torsion-free. If G is torsion-free, then you don't need to care about this. Here you just take the standard action on the Kerry
groups of not suitable? Or any non-secretary?
Well, because it may be elementary, for example, every amenable subgroup. Well, in the free group.
Yeah.
No, in the free group, every non-cyclic subgroup is suitable. That's right. In the free group, but that's you know, in the torsion-free hyperbolic group, same holds true, right? So in some sense, it's a very general notion, but you just have to exclude some pathological things which can happen in acylindrically hyperbolic settings. For example, in acylindrically hyperbolic settings, S can be, I don't know, soluble, amenable, non-cyclic. Okay, so and now I continue the theorem, let S be a suitable subgroup of G, and let T be a finite subset of G. Then there exists a quotient group of G. So there exists an epimorphism from my group G onto a group Q. Let's call it epsilon, such that first Q is acylindrically hyperbolic. Second, the restriction of epsilon onto the ball of radius, so you take the ball in the group G around the identity element of radius m, and this is for every natural number m, there exists epsilon. So what is this? Let me write it down. So the ball of radius n around the identity element in G is the set of all elements G in G such that the length of G with respect to the generating set X, which is specified in the theorem, is at most n. So this restriction is injective. Number 3, well, now we want some good properties, and at this point it may not be clear why we need them, but I'll show you 2 applications where you will see how this property works. So epsilon of T is contained in epsilon of S, so that's what we need the small constellation theory for, and I'll explain how to how to get this condition. Number 4, well, you can add a number of other properties. The one which I'll use today is that if G is torsion-free, then so is Q, the quotient. So now let's first compare this theorem to this theorem. Well, there are no sufficiently independent conditions, right? There is nothing about these relations at all. And these relations, they only occur in the proof of the theorem. So the proof, which is not the real proof, of course, is this. You take, if S is suitable, then we can find independent lexicodromic elements. And again, you have to be careful. It's not enough just to find any 2 independent lexicodromic elements. You have to find independent lexicodromic elements with some technical condition, which I don't want to talk about. Say A and B in S. And then if T consists of elements T1 and so on Tk, remember T is our finite set, you impose the U relations of the form Ri equals Ci Wi of AB, where Wi of AB are small constellation words in the alphabet AB. So again, this is not a classical small constellation like C'16. There is something which is a little bit more complicated, which has 5 parameters, and I don't want to talk about that. But the idea is basically this. So if you find two sufficiently independent loxodromic elements, then you can always pick words Wi of AB so that these relations Ri, R1 and so on, Rk, of this form satisfy this sufficiently independent requirement. Okay? And then the quotient group has all the good properties, which we will discuss in a minute. But right. So you need S to be suitable just to pick this nice loxodromic elements. And it's clear that after imposing all these relations, so my group Q will be G modulo R1 and so on Rk. It's clear that after imposing all these relations, what you get is that Ti equals Wi of AB in the quotient group. In particular, Ti in the quotient group will be inside S, right? So that gives me this condition. Okay? That's what I need. Why I want this condition will be clear in a minute. So now let's go over other conditions. Q is acylindrically hyperbolic. Well, that's the implementation of this hyperbolic-like thing. And again, you need small constellation C to prove that it's sufficiently hyperbolic, well, acylindrically hyperbolic. This condition, second condition, it's an implementation of this locally looks like G thing. Okay? So not only it can be made injective on finite sets by taking n sufficiently large, there is nothing about finiteness of x in this theorem. So sometimes you can find x which is infinite and contains things you want to preserve. Then this ball is also infinite, and all things you want to preserve will be preserved in the quotient. This is a very helpful thing. We already discussed that, and well, this is just one example of a nice property which you can transfer from G to the quotient. So now I just want to tell you how to use this theorem. Now we can forget about small constellation conditions and everything. And it turns out that this simple theorem can be used to prove nice things about acylindrically hyperbolic groups. And you don't really need to know how to construct this small constellation words and all the technical things. Okay, so the first result I want to prove using that theorem is that every acylindrically hyperbolic groups is SQ universal. And let me remind you what SQ universal means and why we care. The group G is called SQ universal, which is the term suggested by Peter Neumann, and SQ stands for subgroup and quotients. If every countable group is a subgroup of a quotient of G. So every countable group is a subgroup of a quotient of G, and that's why it's called SQ universal. In some sense, it means that your group is algebraically large. Let me first discuss a couple of easy implications which follow from the fact that the group is SQ universal. Then I'll explain why every cylindrically hyperbolic group is SQ universal, and it's a simple corollary of this theorem. And then I'll explain that even in the case of, say, mapping class groups, you get some new results. So this is not just some abstract property, but you can derive several results which were known before, even in the case of mapping class groups. But what you get is something which is much stronger. So first of all, let me tell you a couple of remarks. And well, the first remark is that if G is SQ universal, then the free subgroup on two generators embeds in G. Every SQ universal group has free subgroups of arbitrary rank. It's enough group for rank 2, right? Why? Because F2 must embed in some quotient of G. But then you just take the pre-image and it's a free group, right? You have a two-generator group which maps onto a free group with two generators. It must be a free group itself. So, and second thing, if G is countable, then it has 2 to the I of 0 normal subgroups. Why is that? So this is an exercise, and here's the hint. There exists 2 to the I of 0 non-isomorphic finitely generated groups. So why, well, that's well known, right? Why this implies this? Well, in every single, so G is countable. So every quotient of G is countable, right? If you have a countable group, how many finitely generated subgroups does it have? At most countably many, right? So in every single quotient of G, there is a room only for countably many subgroups. But every group from this set, which should embed by the definition of SQ universality, in some quotient of G. And there are uncountably many of them. So there must be uncountably many quotients, right? So it's just cardinality reasoning, which is very simple. So in particular, this gives you some restrictions. What? Questions? No. So in particular, this gives you some restrictions. Well, for example, amenable groups cannot be SQ universal, right? Or say SL2 cannot be SQ universal. Why?
Is that a non-spectrum?
Yes.
Normal subgroup theorem.
Yes, because of the Margulis normal subgroup theorem. Every normal subgroup in SL3C is either finite or finite index, therefore there are countably many of them and predicts number 2, right? What are examples of SQ universal groups? Well, the first, historically, the first example was given in the paper of Hickman, Neumann, and Neumann, where they introduced H&N extensions and proved some embedding theorems. And they proved that F2, they didn't use exactly this term, SQ universal. It was introduced by Peter Neumann later, but what they proved is that F2 is SQ universal. I think you will recognize this theorem if I restate it. So it's equivalent to saying that every countable group can be embedded into two generators. So that's the first embedding theorem. Every countable group can be embedded in the group generated by two elements. And that's actually exactly this statement, that every countable group embeds into the quotient of F2, right? Which means that F2 is SQ universal. Then there were lots of papers about SQ universality of small constellation groups, some groups of geometric origin, for hyperbolic groups, it was proved by Olshansky, and then for relatively hyperbolic groups, and so on. So let me explain why every acylindrically hyperbolic group G is SQ universal. This is a very easy corollary of this theorem. So all what you need, so first of all, well, because of this theorem, because every countable group embeds in the finitely generated group, you don't need to say countable in the definition. It's enough to say finitely generated, and it's the same notion, right? Because of that theorem. Every countable embeds in the finitely generated. If every finitely generated embeds in your group, you're done. So it's enough to show that every finitely generated group embeds in the quotient of G. So let H be a finitely generated group generated by, say, C1 and so on, Ck. And we want to embed H in the quotient of G. So let's take the free product. Let me denote this group by K. My notation. So let's take the free product. A star H. So now if A was acylindrically hyperbolic, then this group is also acylindrically hyperbolic. So this group, now I denote this free product by G. It's very easy to see that it is acylindrically hyperbolic. And the group G is suitable